Hello everyone, my name is Paul Helling, and today I'm presenting on a comparison of priority class distributions for scheduling algorithms. This is work that I did in collaboration with Aspen Olmsted, and we are affiliated with the College of Charleston. This presentation is being used to fulfill the requirements of CSIS 614 at the College of Charleston and has not yet been submitted to any conferences. To give you an overview of my presentation, I will give a brief introduction to schedule processing, pose the question I'm trying to answer, and share my methodology, preliminary results, and initial conclusions. I want to open my presentation with why I studied process scheduling. First, scheduling has many applications in the domains of computer science and information technology. Academic research papers on the topic often cite a wide range of applications for their work, including cloud computing, platform as a service, and real-time embedded systems. Scheduling can also be used to manage network traffic and guarantee quality of service. I'll explore some of these applications further in the related works section of this presentation. Second, scheduling is difficult. There's not one right way to schedule processes, which is why there's so many algorithms and researchers are still proposing new ones. As far as scheduling processes is concerned, some traits of a good scheduler include maximized throughput, a lack of indefinite blocking, minimized overhead, enforced priorities when applicable, and a balance between system response and CPU utilization. Based off these traits, it's also possible to identify some key metrics of a good process scheduler. An ideal scheduler should minimize context switches, turnaround time, and waiting time, and it should maximize throughput and CPU utilization. Other papers that I looked at referenced other metrics like approximation ratio and resource augmentation. But what I liked about these metrics here is that they're simple, easy to understand, and easy to calculate, which makes them good for a preliminary simulation experiment. Now that I have gone over the importance of process scheduling, I want to give a brief overview of scheduling algorithms. I'm also going to give a disclaimer here as well. This is just an introduction to process scheduling, so multiprocessor scheduling and a full taxonomy of scheduling algorithms are beyond the scope of this presentation. Scheduling as a trait can vary in several ways. Iterative schedulers schedule iteratively or step by step, which is how most simple algorithms like round robin or any other algorithm that doesn't have real-world time constraints operate. Real-time schedulers include those that not only must complete a task, but also complete it at the correct time, such as an earliest deadline first algorithm. The distinction between centralized and distributed schedulers is generally only relevant on a network scale. Centralized schedulers have one point of failure, but distributed schedulers generally refer to those that coordinate work between several computers. Priority can be fixed or dynamic. Dynamic priorities can be helpful by allowing low priority processes to gain priority over time, ensuring their eventual completion. Schedulers can also vary in how they handle the arrival of high priority tasks. Preemptive schedulers can be interrupted to work on high priority tasks, but non-preemptive ones cannot. Cooperative means that processes can only be preempted at certain points. In terms of algorithms, priority-based scheduling algorithms are the subject of this presentation, but other notable classes of algorithms include round robin, first come first served, shortest job first, and shortest time remaining first. Several publications use a weighted round robin algorithm that incorporates elements of priority-based scheduling into the traditional round robin algorithm. I didn't find a lot of information about priority classes, so the other works I looked at used priority-based scheduling and often employed a novel algorithm. The first proposed a multi-objective task scheduling algorithm. Since cloud computing service providers often have multiple data centers, the service provider needs to manage these data centers to ensure quality of service for the customers. So the algorithm matches tasks to virtual machines. To avoid the problem of long wait times caused by certain processes being consistently preempted in a traditional priority-based or shortest time first scheduling algorithm, this new algorithm takes both factors into consideration. Because this study was dependent on simulating network traffic, they used software called CloudSim to model the performance of their algorithm. Another study I looked at also sought to improve the performance of cloud computing systems, recognizing that process scheduling in cloud computing systems is complicated. The authors used a genetic algorithm to help solve this problem. The details of the crossover mutation operations aren't particularly relevant to priority-based scheduling, despite being the bulk of the source publication, but I was interested in the simulations they used and the model verification process. They generated application graphs with 10, 20, 50, and 100 subtasks to be scheduled by their algorithm. They also validated the model's behavior, showing that it is reachable, fair, and deadlock-free. There is very little research on priority class distributions. For instance, how should priorities be assigned? Many algorithms use discrete values and can differ in how many different values are recognized. But in a multi-objective algorithm that combines priority with time remaining, should these new priorities still be discrete? Additionally, based on work I've done in other fields, I've observed power law properties in metadata in many datasets, and these properties are particularly well documented in language, fractal mathematics, and music. Could a priority distribution with power law properties result in a better scheduler performance compared with normal or uniform distributions? To answer these questions, I simulated a priority-based scheduler using Python. I created 6 different priority distributions: uniform, normal, and power, each with discrete or continuous values. I also tested the performance of the schedulers based on 4 different scheduler metrics: context switches, waiting time, and turnaround time, which should be minimized, and throughput, which should be maximized. For each priority distribution, I tested 5,000 schedulers that each followed the same algorithm, but differed in the processes they were scheduling. Each scheduler had 20 randomly generated processes, where the priority of the process followed one of the previously determined priority distributions, and the arrival time and total burst time followed uniform distributions with limitations on the maximum values. To test whether or not priority distribution had an effect on the different metrics I collected, I used the Kruskal-Wallis test. This is because my data was not normally distributed, which I verified with statistical testing, which meant that I could not use an ANOVA to test the effects of my different conditions. Lastly, because of the limitations of my computer and the algorithm I was using, I had to take samples from waiting time and turnaround time to calculate those values. That's because for context switches and throughput, each scheduler has one value, so there's only 5,000 values. But each process has its own waiting time and turnaround time, which meant that to do the Kruskal-Wallis test on those, there were 10,000 samples, which was too much. And so that's why I took a random sample of 5,000. And then lastly, I did post hoc tests as necessary to see what the effects were. Like I said previously, I used the Kruskal-Wallis test in my analysis, and this test tests the null hypothesis that the population median of all the groups is equal. And it does work on 2 or more independent samples, which is an important consideration for me since there are 3 different samples in this 3 different independent samples in this study. And then rejecting null hypothesis does not indicate which of the groups differ, which means that post hoc tests are required. I ran the test by grouping the data sets by metric and then by whether or not the priority classes were discrete or continuous. So only the scheduler metric of context switches had a low enough p-value, and again that was only for the discrete priority class distribution. So I did post hoc testing on those data sets. For further clarification, the 3 data sets included in that test were the number of context switches for uniform discrete, normal discrete, and power discrete. After carrying out the post hoc statistical tests, the pairwise comparisons of the 3 different independent samples, so uniform distribution, normal distribution, or power distribution, showed that that each distribution did have a p-value of 0, so they were each distinct distributions. And so in light of that, I wanted to compare the context switches for the continuous and the discrete data set side by side in this table. And so although the means and standard deviations of the number of context switches overlap in the discrete data sets, these results are in fact statistically significant. Additionally, these results suggest that discrete priority classes have fewer context switches than continuous ones, and that a normal distribution of discrete priority classes has the fewest context switches. Most of my study's problems result from the fact that it is a simulation instead of an actual experiment. In particular, many of the more powerful statistical tests do make the assumption that the data is normally distributed. And so I did find, based on other statistical tests, that my data was not normally distributed, which was expected because I used the default random number generator, which is a uniform generator, to generate the arrival times and burst times for the randomly generated processes. And then one of the other problems with doing the simulation experiment is that there were a lack of benchmarks for simulating processes. For example, how many processes will a scheduler see over the course of a certain amount of time, or how long do processes last? And so in this study, I had sort of made some loose assumptions that each scheduler would see 20 processes, which was consistent with the amount of samples used in other studies that I looked at. And then for how long the processes last, I just sort of assumed that a maximum duration of 10 bursts seemed like a reasonable place to start. There are a number of next steps I could take to improve this experiment, this study. So naturally, I could improve the simulations for the schedulers and processes based on the problems identified previously. So for example, if I could either collect some data myself on how many processes does the CPU see, or how long they generally need to last, that could provide valuable information for making a more accurate simulation. And then also, another thing I could do is statistically validate the simulated data. And so something that I've noticed is the random number generators are inherently stochastic, and so there is variation in the p-values that are calculated if the program is run several times, and I found this out over the course of testing. And so I'd assumed that by having 5,000 schedulers for each distribution, each with 20 processes for 10,000 processes total, I'd assume that sample sizes that large wouldn't be quite as variable as they seem to be based on the results of the Kruskal-Wallis test and some of the other tests that I did. And so definitely looking into statistical tests that can validate the independence of the data would be a useful next step. And then lastly, I could try other algorithms and see how they perform with the different priority classes. Because for the purposes of this study, since this is sort of basic fundamental research and priority class distributions, I just use the simplest priority class algorithm. But given some of the more complicated ones that I covered in the related works and other ones that I've seen while preparing for this project, I could try to adapt a number of those to see how they perform with the different priority class distributions. So in conclusion, the normal distribution of discrete priority classes showed the fewest context switches, which means that that may be a suitable priority class distribution to use for future research to develop improved priority-based scheduling algorithms. And then the other the other conclusion is that priority class distributions with power law properties do not result in improved scheduler metrics compared to the uniform and the normal distribution of priority classes. And lastly, but not least, these are the references that I used while I was completing this research project.